Okay, hello to all. My name is Ilkka Heikura and I'm here to talk about a bit about antenna design for radio modules. So here is my background. So about 17 years of expertise in designing antennas for many different kind of devices, mobile phones, laptops, smartwatches and so on. Started at 2007 at Pulse Electronics and currently working at Bittium Wireless as a senior antenna specialist. Here's a bit what we are going to discuss today. Some wording about who we are at the Bittium and then about the antenna effect on radio link budget and so on. But first about Bittium. So I don't know, have you heard of us before? But we are a high-tech company specialized in secure connectivity, R&D services, and tactical communications and medical technologies. And this year it's our 40th anniversary of expertise in advanced radio communication technologies, and we have around 600 employees, and our headquarters is in Oulu, Finland. First of all, some motivation for this presentation. So about the antenna effect on radio link budget. So antenna itself is one of the most important things that define the connectivity of your device. So when you are using radio modules, you have a pre-certified module with some transmission power and some reception sensitivity, and then you have the antenna, and you have some gain for the antenna, and then when the radio transmits over the air, the signal is attenuating because of free space path loss, for example, and then you have the receiving end there and some antenna with gain, which then improves the reception, and then that's why the antenna is one of the key parameters that defines the communication distance. And the difference between good and bad antenna can be huge, over 10 decibels. And this doubles if the same antenna is in both ends of the radio link. And in general, in free space, if you increase antenna gain 6 decibels, it doubles the link distance. And in cellular configuration, this means up to 4 times cell size. So main antenna performance parameters to be considered are the radiation efficiency, gain and directivity, and the polarization of your antenna. So when thinking antenna design as part of the device, industrial and mechanical design, you can go with commercial off-the-shelf antennas, which you usually see in wireless routers, and then custom antenna design, for example, in these smartwatches or sport watches. Custom antenna design usually enables more ambitious industrial design than these off-the-shelf antennas. So this consumer attractive industrial design creates a huge challenge to antenna design, because the antenna usually, or the device needs to be as small and slim as possible, and additional space for antennas is wanted to be avoided. And many times the device also needs to be durable and rugged. So the space for the antenna is minimal, and in these cases you want to consider using the outmost metals or surfaces for the antenna, as you usually see, for example, in your smartphone. So the outmost metals are acting as part of the antenna, or are directly the antenna that is used for cellular or other communication. With 3D manufacturing technologies like LDS, antennas can be almost in any surface and can be integrated to enable smooth ID. One thing that you should think about when you are developing your device is that is the device sold worldwide? There's a lot of different frequency bands in cellular connectivity, starting from 600 megahertz up to 3 point something gigahertz, or up to 5 gigahertz in 5G networks. So you need to think that and check that which operating bands are supported by your modem. So if you are designing a device, for example, to US market, there's no point of selecting the kind of modem that supports all the bands in the world. So in these cases, you can design your antenna just to support only the US bands, and most of the cases the antenna design can be smaller and require less space from your device. For supporting worldwide connectivity, you might think that you can support all the necessary bands with one antenna design, but when you do this, you tend to increase the complexity of the matching circuitry for the antenna, and by doing this, you also increase losses from that circuitry. And failing to meet regulatory or operator approvals can lead to regional antenna designs. One option is also to use active antenna tuning, and that means that you have like a capacitance bank or switches that then tune the antenna to different operating bands via GPIO or MIPI interface. So how does the design process go in our simulation tool? At Bittium, we are using CST Microwave Studio. And first of all, we like to get involved with the antenna design as early as possible. And that means already in the concepting phase, when you are thinking that what kind of connectivity do you want to have in your device, and what operating bands needs to be supported. So at first, the 3D CAD model of the device is imported to the software, and then we can modify the 3D model in many different ways. After importing, we are defining the materials to represent the mechanical structure. And in this simulation tool, we have a large material library built in, and we can add different kind of materials also to this library. So if you have like very exotic dielectric materials, we can add the parameters of those, and those can be used while evaluating the antenna performance. Then the antenna is designed or implemented to given space. And by implementing, I mean that if you are using like off-the-shelf antennas, like FPC antennas or chip antennas, we take the mechanical and electrical model of this antenna and then implement it to the device. And at first, the simulations are done in free space scenario, and by free space scenario we mean that there's no dielectric or conductive materials nearby the device. This is very fast way to evaluate the first performance and design of the antenna, but also we can have like human head and hand and many different kind of other scenarios there, like body phantom parts, or install the antennas in base station towers, airplanes, and so on. We can also simulate the matching circuitry with real component parameters, and we can also implement the layout of the PCB to enhance the accuracy of the simulated performance. When all of these things has been done, the simulation results are compared to given targets, and if those performance targets are not met, then we make changes to the design. As the antenna design is iterative process, so changes can be done to components, and those do not cause issues while simulating in this kind of a virtual environment. So what do you need to take into account when you are designing antennas? So first of all, the main thing is that the antenna needs to be taken into account already in concepting phase. Many times customers come to us and they have built already the first prototype and they are having connectivity issues, and then they have not reserved enough space for the antenna, or the dielectric materials around the antenna are selected so that the antenna is not tuned correctly, and or the dielectric material is causing too much losses to the performance. When we are talking about dielectric materials, dielectric constant and dielectric loss are the most important things that we take into account. Dielectric constant of plastics usually are in between 2.5 and 3.5 at 1 gigahertz, and with ceramics above 20. And we are preferring to have less than 0.01 loss tangent at 1 gigahertz frequency. Then the conductivity of the metal is one key factor. If you are using very poorly conductive metals, your antenna performance will be degraded. So use high conductive metals like copper or aluminum or so on. This size of the ground plane is one of the key factors, and the lower the frequency is, the bigger the ground plane should be for high performing antennas. For example, the recommendation is that to have at least 1/4 of the wavelength of the lowest frequency, and at 700 megahertz it's already 11 centimeters. Distance to surrounding metals is one thing which affects to antenna performance, bandwidth and directivity. So if you have a ground plane very close to your antenna, the antenna most likely will have a narrow bandwidth, and the directivity is high. So you just direct the radiation pattern in some certain direction, and then you lose the connectivity in other direction. For example, in these wireless routers where you have these external antennas like dipoles, and if you place it against metallic wall, it will direct the radiation and then you don't have any connectivity behind that device. Grounding of the metals is very important thing because the electromagnetic field couples to slots, gaps, and metallic parts. But sometimes these kind of things can be used also as part of the antenna, and then to enhance the connectivity. For example, if you have a sport watch from Garmin, Polar, or some other brand, you may find that there's this kind of metallic ring around the display. So most probably that ring is used as an antenna or as part of the antenna to enable the satellite connectivity or better performance for that GPS antenna. It is important to have sufficient amount of grounding points to avoid non-radiating resonances in operating bands. And one good rule of thumb is that one grounding point within every 1/10 of a length of a wavelength. And then if the length of the metallic object is less than 1/4 of the wavelength of the highest operating frequency, or if it resonates at unused frequency, it can also be left electrically floating. So here we have a picture of one mobile phone antenna. We have some antenna traces here, then NFC antenna there, then there's some metal, supportive metal there, and some grounding gasket there. So these grounding gaskets are there for a purpose, to prevent non-radiating resonances from some parts of the device's structure. So here is an example of effect of dielectric properties, and in this case a dielectric constant. So I simulated an LTE antenna with dielectric constant of 1, which represents vacuum. And in this case, this is like a FPC antenna. So when it is not adhered to any plastic, it is correctly tuned to support frequencies from about 800 megahertz up to 960 megahertz, and from 1700 to 2700 megahertz. But as soon as you adhere this antenna to plastic with like dielectric constant of 2, the antenna will detune to lower frequency, and you lose connectivity at the 900 megahertz area. And the higher the dielectric constant is, the lower the antenna tuning will go. So bear this in mind when you are selecting or selecting materials that are nearby your antenna, and then take into account that this might be one of the reasons why your connectivity is bad when you are implementing off-the-shelf antennas. These antenna manufacturers many times describe the environment where the antenna has been measured when the performance specifications, where the performance specifications has been measured while making that data sheet. So please check the data sheet. Another thing is the loss tangent of the dielectric material. So this is the same antenna as earlier. So first of all, it has been simulated in lossless environment, but as soon as you have dielectric material in close proximity, or the antenna has been adhered to plastic, you introduce losses to the performance, and already with a loss tangent of 0.01, you are losing like 0.1 to 0.2 decibels of your antenna performance. And the higher the loss is, the more losses to your antenna comes. So especially when you are working with low frequencies, this comes important, as the lower the frequency is, it is more challenging to design high performance antenna, and then when you are fighting for every tenth of a decibel, you want to think that what is the loss tangent of my dielectric material where the antenna has been adhered or designed to. About active tuning, so there are two kind of scenarios. You have aperture tuning or impedance tuning. So in aperture tuning, the antenna or the tuning part is part of the antenna. You may have one additional contact for the switch, or you may have it as part of the matching circuitry. This is a valid point when the environment where the antenna needs to be designed is very limited, and the antenna cannot be matched to all needed frequency bands with high performance. And most of the high-end mobile phones are using some kind of active tuning to support the worldwide connectivity of the device. When you are using this active tuning, the whole frequency band can be covered with one tuner state, or the frequency range can be divided into smaller portions for optimized performance. And for example, in these mobile phones, they are using very high-end antenna tuners, which can be also characterized for many different kind of use cases, like when you are holding your hand, the device in your hand, it has different tuner state for that, and if it's close proximity to your body, it has different tuner state for that. And for example, one mobile phone from recent years, it had like 60 different states to cover one LTE operating band. Okay, about antenna integration. So off-the-shelf antennas are very attractive to be implemented in the device, and are one of the easiest ways to add multiband connectivity, for example, to evaluation port or macro port. And these antennas works very well when they are implemented in the same way as described in the datasheet. So when you are putting mechanics around these antennas, the environment is different. And these surrounding metals and dielectric materials are having effect to antenna matching, tuning, and bandwidth, as we saw already with the examples of dielectric properties. And then, yeah, the shape and size of the ground plane is affecting the antenna, especially these small chip antennas, because these chip antennas are designed to wake up the ground plane resonance, and the ground plane is the main source of the antenna radiation. These radiation characteristics, what has been mentioned in the datasheet, can be very different if the chip antenna is implemented in different location on the PCB than what has been shown in the datasheet. Here is example of that. So I took one chip antenna where the ground plane size in the datasheet was 48 by 20 millimeters and simulated it in different implementations. So on this first graph, this is showing the antenna S parameters or antenna tuning in decibels. And this red curve here is the S parameters with the evaluation board that was mentioned in the datasheet. So it is covering Wi-Fi frequencies from 2.4 gigahertz to 5 gigahertz. And if you shorten the PCB length, well, you have good connectivity or in 5 gigahertz band, but most probably your 2.4 gigahertz band performance will be sacrificed. If you place ground plane on both sides of the antenna, then you will lose connectivity or have bad connectivity at 5 gigahertz, but also at the 2.4 gigahertz. Then one thing that we see very often when customer comes to us and say, hey, I have a bad performing antenna and my connectivity is not on a desired level. We see that they have against the design rules, they have placed ground plane under the antenna. Okay, so what happens is that you don't have any radiating resonances at 5 gigahertz band, and the 2.4 gigahertz band has moved about 500 megahertz lower frequency. So you have poor connectivity on both frequency bands. Well, then if you have the ground plane only halfway under the antenna, well, you get some radiating resonance at 5 gigahertz band, but most probably the performance will be bad. And still your 2.4 gigahertz band will have very poor connectivity, as the antenna is around 300 megahertz lower frequency than it should be. Then I also simulated the case that you add plastic covers around the PCB. And these plastic covers were having dielectric constant of 3 and loss tangent of 0.01. So you have good connectivity on 5 gigahertz band, but you lose some of the performance at 2.4 gigahertz, as the antenna is more or less like 150 megahertz low tuned. About custom antenna integration, so here is a picture of a mobile phone that we designed for Mexican government, and this is the satellite connectivity antenna and its radiation pattern that has been simulated. So there are many different things which prevent usage of the off-the-shelf antennas. For example, weight. If you have like a drone and you want to have longer operating time, you may not want to choose the kind of GPS antenna which has high weight. For example, this stacked patch antenna weighs 25 grams, and then it can reduce the flying time of the drone. Then the available space. shape of the device and the materials what you are using. So the custom antenna design gives freedom to design the antenna to fit to the given space. And there are many different 3D antenna manufacturing technologies available. LDS, LEP, LAP are laser technologies. Fluidant is conductive ink, and there are many others also. But also traditional technologies like sheet metal antennas and flexible FPCs can be used. Antenna needs metal-free area around it, so the lower the frequency, the greater the distance is needed for wideband operation. One thing that you want to consider when designing antennas is the antenna performance in real use case versus the performance in free space. Because so the free space antenna, free space performance is that when you don't have any dielectric or conductive materials around or nearby the antenna. And in real use case, you may have human head and hand or some body part, and these are the kind of things that will have an effect to your antenna performance. For example, human head and hand usually decreases the antenna performance by 6 to 10 decibels. And as you may remember, 6 decibels already either increases or decreases the connectivity distance to half or double. The body decreases the antenna performance, but also affects the radiation pattern as the body directs the radiation away from the human body. And also metals are directing the pattern. So therefore, it is highly important to design the antenna of the device so that it is having best possible performance in real use case. Because what do you do with the antenna which is performing very well in free space if it doesn't work in the real use case? Okay, and then 5 things to remember is that take the antenna into account already in the concepting phase, because that's when you have the possibility to affect to the device's internal mechanics, for example, and then optimize the antenna for the main use case of the device. And every detail in the design matters. So grounding points of the metals, lengths of slots and metallic parts. And read the datasheet carefully when integrating these off-the-shelf antennas. Because that's where things go wrong many times, that you don't read that datasheet carefully and you integrate the antenna in wrong way. And we, as a Bittium's experts, can help you with your antenna design if you face challenges. And if you have more questions during today or tomorrow, you can come to visit us at booth A6. Okay, thank you.